Welcome to the video lecture on composite graphs with transformations. We're going to start with a few examples that are just some basic transformations, but they're a little bit tricky because they have several different things going on at once. So first thing I want to remind you of is that when you're looking at a function, for example this number 1 right here, the first thing you want to do is always remember to factor out any coefficient that you have in front of x. In this case, there isn't any other terms next to that x, so this 4 is considered factored out. But when you look at something, for example, like number 3 down here, you would want to factor out this 3 from the x and from the 9 both before you figure out what your different transformations are. So always look for that at the very beginning. In addition, and in this example up here for number 1, right now this 4 is acting like a horizontal compression by a factor of 1/4. And usually I find it a little bit more difficult to graph things with horizontal stretches or compressions. So I personally like to change things to vertical stretches or compressions if it's possible to do so. And you can do that on this example because square root of 4 reduces nicely to a 2 that you could pull out. So in other words, we could change this to 3 times and then change that square root of 4 to a 2 and leave that x under the radical, and then this 3 times 2 just becomes 6 square root of x minus 2. So if you look at this equation now, there's no more horizontal compression going on. Instead, this 6 becomes a vertical stretch by a factor of 6. And the 2 on the side, that minus, tells us that we're going to go down 2. So those are the only two different transformations that we have going on. Now you do want to recall what the graph of square root of x looks like, and we had a function library that showed us all the different types of graphs that you're expected to know. And square root of x is right here. And remember, our pattern for this is normally it's starting at the origin and then you would go up 1 over 1 and then up 1 over 3. So that's what we're going to be using on our graph here, but because we have some transformations going on, some of those things are going to change. So instead of starting at 0, we do have a vertical stretch, but before I figure out that stretch part of it, remember that the stretch isn't going to change that starting point. If you're starting at a height of 0 and you stretch that by 6, you're multiplying that height of 0 times 6. 0 times 6 stays 0. So this initial point doesn't move because of the stretch, but it does move because we're going down 2. So my very first starting point, instead of being at the origin, is going to be down here at -2. Then the stretch is going to come into play when I start doing my pattern. Normally, we would want to go up 1 over 1, but because we have a vertical stretch, instead of just going up 1, now we need to go up 6. So we're going to go up 1, 2, 3, 4, 5, 6. We're just stretching in the vertical direction, so that 6 tells us how high to go, but we still only need to go over 1 because we're not changing our horizontal direction at all. Then from there, we would want to go up another 6, 1, 2, 3, 4, 5, 6, and over 3. So instead of going up 1 over 1, we went up 6 over 1, and then instead of going up 1 over 3, we went up 6 over 3. So still the same pattern going horizontally, but slightly higher values going vertically. And when I connect my dots, there's my graph. Okay? Let's try another example. Here we have negative parentheses 1/2 x quantity cubed plus 1. Now if you want to do the same kind of idea that we did in the last one, you certainly could here. You could take that 1/2 and you could go ahead and cube it and turn it into a 1/8, and then it would just be the x that's getting cubed. If you think of it this way, then this would be a vertical compression by 1/8. We've taken that 1/2 out of the parentheses, cubed it, and pulled it out, and now we've turned it into a vertical compression. Because we did that in the last example, I want to show you how you could do this if you just treated it the way it was originally. So This time around, I'm going to show you how to graph this, leaving that 1/2 inside the parentheses and thinking of this as a horizontal stretch in this case. Remember that horizontal direction is sort of opposite of what you would expect. So if you see a 1/2 in there, you're actually going to stretch by the reciprocal of that. So we're going to stretch horizontally by a factor of 2. So this graph has that horizontal stretch by a factor of 2. It also has, because of that negative on the outside of the cube, on the outside of the parentheses, there's also a reflection. And when it's outside, that's a vertical reflection over the x-axis. And we have the +1 on the side, so that's going to be going up 1. Okay, so we're going to ignore this direction, and instead we're going to think in this direction instead. So we're going to think horizontally. So let's see what that would do to our graph. Now, x cubed, pull up our function library here for a second. Here's what x cubed looks like, a nice polynomial graph centered at the origin, and the pattern here would be over 1, up 1 to the right, or over left 1, down 1 to the left to get a couple of side points. And if you wanted a few more side points, you could go over 1, up 7, or over 1, down 7. Okay, so that's sort of the pattern that we're going to follow. But instead of starting with that, let's kind of do this in a progression here. Normally, we would want just an x cubed graph to go over 1, up 1, over 1, down 1, over 1, up 7, over 1, down 7. So it would have this kind of shape to it. How is that going to change if I put a minus in front, if I do a reflection over the x-axis? Well, then it's just going to change direction. So instead of going over 1, up 1, we're going to go over 1, up 1 on the left, and over right 1, down 1 to the right, and over 1, up 7, over 1, down 7 to get a couple of side points in addition to our ones in the middle. So this is what our negative x cubed graph would normally look like. Alright, so we've taken care of the negative. How about this horizontal stretch by a factor of 2? How is that going to change this pattern? Well, we're thinking horizontally. So instead of just going over 1 to the right, now we want to stretch that by a factor of 2. So now we're going to want to go over 2 units to the right and then go down our 1. And instead of going 1 to the left, we actually want to go 2 to the left and then go up 1. So we're stretching out this graph like this. So this one in black would be the equivalent of still having that negative in there because this is a decreasing graph, but now we've introduced that 1/2 being multiplied by our x. So this graph in black is negative parentheses 1/2 x quantity cubed. So all we did was stretch out horizontally our point before we dropped it down 1, or stretched it out horizontally before we bumped it up 1. And you could do that additionally on the sides as well, but I think we have enough to deal with so far with these 3 points. Okay, we're almost done. We've got the horizontal stretch taken care of. We've got the reflection taken care of. Now all we have to do is move everything up 1. So let's create a new graph for that. And all we're going to do is take this key point, and this key point, and we're just going to move those up 1. So instead of being centered at the origin, now it's going to get shifted up 1 and be centered at 1 on that y-axis. And then we're going to do that horizontal stretch to the right 2 before we drop it down 1. So that's this point being shifted up 1 unit. And then from that center point, we're going to stretch it horizontally to the left and then go up 1. So that's this point moved up 1 unit. So here's our 3 key points, and if I connect them into that nice cubic shape, you have your graph. Okay? So now all 3 transformations are finished. Okay, let's try another example. This one's an absolute value. Now this is one where you have this 3 in front of your x, So what you want to be careful about is making sure that you factor out that 3 first before you decide what your horizontal shift is to the left or to the right. If you just look at this and you say, oh, I see a +9, that means I need to go left 9, then you're going to get this graph wrong. Because what you need to do first is take that 3, factor it out, so you're going to be left with an x plus 3 in parentheses. And then if you want, because this is an absolute value, you can figure out what the absolute value of 3 is. It's still 3. So this 3 can actually get pulled outside of that absolute value if you want to. And I personally like to do that because if you leave it in, then that's thinking in terms of a horizontal compression, which I find a little bit tougher to graph, versus if you pull it out, now it becomes a vertical stretch by a factor of 3, and I like to do those better. That's just my personal preference. You don't have to do it that way. So if I pull out that 3, then this means I have a vertical stretch by a factor of 3. That's because of this 3. The 3 on the inside is positive, but we want to go in the opposite direction, so this is going to be a horizontal shift left 3, and then the -2 on the end means we're going to go down 2. So let's put it all together. Now you should have the graph of an absolute value memorized. It's just a big V shape centered with its vertex at the origin, and the pattern is over 1, up 1, over 1, up 1, over 1, up 1 on each side. So that's what we want to do, but we have to move some things around. Now if you're starting at the origin, a stretch or compression is not going to change that. The only thing that's going to affect that vertex is a shift left or right. So we're going to be moving our vertex left 3 and down 2. So here's my new vertex. Now to get the rest of the graph, we can use our pattern, and our pattern normally would say to go over 1, up 1, over 1, up 1, and so forth on the left and on the right. But because we have this vertical stretch, we're still just going to go over 1, but now we're going to go up 3. We're going to vertically stretch our y's up 3 units from where it normally would be. So 1, 2, 3 is now where that new side point is. And we're going to do the same thing on the left side. Still go horizontally left 1, but now we're going to go up 3 vertically. And if you wanted to do it again, from these points you would go over 1, and then you would go up 3. Over 1, up 3. And now you have a couple dots on either side to give you that V shape. So this graph right here in black is my new graph. Much steeper than a normal V would be because of that vertical stretch. Okay, let's take a look at number 4. Now this is just like number 3 in that it does have a coefficient in front of that 2. So to make sure that you get this correct, don't assume that this -1 is going to be a shift to the right 1. That would be incorrect. You have to factor out your 2 first, and that means that in actuality you're going to be shifting right 1/2 because that's what's left in these parentheses. Now, unlike the last problem where we pulled that 3 out of the absolute value, here I probably wouldn't do that because square root of 2 does not reduce nicely. You can't just pull that 2 out of that square root without it turning into a big decimal, which we don't want to have to deal with when we're trying to graph. So in this problem, we are stuck with leaving that 2 underneath, and because it's underneath the radical, remember opposites, so here this 2 is actually a horizontal compression by 1/2. We do the reciprocal, so we're going to be shrinking those horizontal changes by 1/2. What does the -1/2 inside the parentheses do? Because it's next to that x under that radical, that's a horizontal shift, and because it's minus, we're actually going to go right 1/2. And then what does the +2 on the end do? That's going to tell us to go up 2. So let's put all the pieces together. I'm going to do this in stages because this is a little bit tricky to do, especially with that horizontal compression. So first let's recall what a normal square root graph would look like. Normally it would start at the origin, and then we would go up 1 over 1, up 1 over 3. And we have that nice little arc shape. So there's square root of x. Now let's talk about what the square root of 2x would do. So we're going to introduce first just this horizontal compression by a half. So horizontal compression will not affect that starting point at the origin. That's going to stay put. But instead of going over 1 to the right and then up 1, we're now only going to be going half that distance to the right because of our compression by a half. So here I'm only going to go over a half, but still up 1. Whoops, I did that a little bit too low. Let me fix that. So we're going to go over a half, so right here at a half, and we're going to go up to a height of 1. So this point right here should be 1/2 for x, but still 1 for y. And then we're going to do that again. We're going to go over, instead of normally we would go over 3, remember initially this is a distance of 3 here, and we go up 1, we have to cut that horizontal distance in half. So what's half of 3? 3 halves, or 1 1/2. So now what we need to do is change this so that instead of going over 3 up 1, we're actually going to go over 3 halves up 1. So what's 3 halves the same as? That's the same as 1 1/2, or 1.5. So I need to go over a half and 1 more, and then I'm going up 1. So this dot right here should line up right at 2, because we were at a half before. So when we take a half and we add 1 1/2 to that, we stop at 2. And we were at a height of 1, and we're going up 1 more, so now this should be 2, 2. So this graph should look something like that. So that's kind of tricky, all right? We went over a half up 1, and then we went over 3 halves up 1. Instead of going over 1 up 1, over 3 up 1. Okay, so we cut that horizontal distance in half. All right, that was a lot of work just to get that horizontal compression. Now we still need to move everything right by a half. So let me make a new graph here. We're going to take each of these 3 key points right here, which is 0, 0, this point right here, which is 1/2, 1, and this point right here, which is 2, 2, we're going to move each of those right 1/2. So if I take 0, 0 and I move it to the right 1/2, then it's going to be right here at a half, 0. If I take 1/2, 1 and I move it to the right 1/2, if you're starting at a half and you move it right a half, now you're at 1, but we're still at a height of 1. And this last point was at 2, 2. We're not changing the height, we're just changing the x. And now we're going to take that x and we're going to add a half to it. So instead of being at 2, now it's going to be at 2 1/2. But still at a height of 2. We're not changing the y, we're just changing the x. So this point is now 2 1/2, 2. And this point right here is 1, 1. And this point right here is 1/2, 0. Alright, we're almost done. All we have to do now is do our up 2. So now we're going to tackle that, and that's going to change each of these y values in these 3 points up 2 units. So let's draw what that final graph would look like. If we add 2 to this y value right here, we're still going to be at 1/2 for x, but now we're going to be at a height of 2. For this point 1, 1, we're still going to be at 1 for x, but we're going to add 2 to that y, so now this is going to be up at a height of 3. And for 2 1/2, 2, we're still going to be at 2 1/2 for the x, but we're going to add 2 to that y, which now makes it 4. So you should have the following pattern: 1/2, 2, and that's because we shifted right a half and up 2. So that's why this point is to the right 1/2 and up 2. And then from there, instead of going over 1 up 1, we only go over a half up 1. And then from this point, instead of going over 3 up 1, we go over 3 halves up 1. And that's because of that horizontal compression. So this graph right here is our final answer. Okay, so those horizontal compressions are pretty tricky to do. Okay, let's take a look at absolute composite graphs. So now what we're going to be doing is looking at some graphs and taking the absolute value of them. So we want to think about what an absolute value will do to a number. We know that absolute value turns things positive. So if you are already positive to begin with, then you're going to stay the same. If you're negative to begin with, then you're going to become positive by flipping over the x-axis. So let's see how this would work. So in this first example, what we want to do is start by just graphing what's inside of these absolute values. So let's graph just this rational function, 3x plus 1 over x minus 3. And then we will alter that graph by taking its absolute value. But we have to start with this inside part first. So what do you do to graph a rational function? Well, there's a couple things that you should be looking for. First of all, asymptotes. The vertical asymptotes always occur wherever this denominator is going to be 0, which in this case is going to be at x equals to 3. Then you might have a horizontal asymptote, and that occurs when you look at the dominant term on the top, which is that 3x, over the dominant term on the bottom, which is that x, and those x's will cancel out, giving me 3. So that means I have a horizontal asymptote at y equals to 3. And then you may want to look at some intercepts. An x-intercept is going to occur whenever the numerator is 0. And if you solve that numerator equal to 0, you're going to get x equals negative 1/3. The y-intercept occurs whenever these x's are 0. So if I let this be 0 and this be 0, you're just going to be left with those constants. So your y will be 1 over negative 3, or negative 1/3 as well. So now let's start to put it together into a graph. We know that we have a y-intercept at negative 1/3 and an x-intercept at negative 1/3. So those are two small little points. We have a vertical asymptote at 3, so I'm going to draw a little dashed vertical line, and a horizontal asymptote at 3, so horizontal dashed line. Okay? Now before we connect any points together here, you need to figure out what your end behavior is going to be like near those asymptotes. So when I look at this x equals to 3, remember to look at that denominator and notice what power it's raised to. This is raised to the first power. So that means you have to have opposite behavior on either side of that asymptote. In other words, you either go down on the left and up on the right, or you have to go up on the left and down on the right. It's one or the other. So to figure out which way you should go, you want to look at a test point. So for example, if I'm exploring what's going to happen around this vertical asymptote at 3, maybe we should look at something close to 3 but slightly to the left of it. So something slightly smaller than 3, like 2.9. If I take 2.9 and I plug it into this numerator, what sign is that going to be? Well, 3 times 2.9 is positive something, plus 1 is going to stay positive. So that numerator is a positive value. If I take 2.9 and plug it into the bottom, 2.9 minus a 3 is going to be negative. All I care about is whether this is positive or negative. So a positive divided by a negative stays negative. So what this means is as x goes to 3 from the left side, because we were looking at something smaller than 3, the y values are going to be going to negatives, and they're going to be shooting towards negative infinity, because that's what happens with a vertical asymptote. As your denominator gets closer to 0, the whole fraction gets really, really big or really, really small. So in this case, we're getting really, really small. So what this is going to look like on my graph is as I approach this direction, my graph needs to be shooting down towards minus infinity. Now you don't need to bother picking a test point for the other side because you know it has to do exactly the opposite behavior. So if I'm going down on the left, then I have to be shooting up on the right. So that's not a whole lot of information, but it should be enough to kind of plot your rational function. We know that since this is shooting down, it's going to have to come up here and pass through my two intercepts, and then I'm going to eventually level out towards that horizontal asymptote. So my graph is a little bit curvy here, a little bit out of shape, but use your imagination there. Then on the other side, same thing. I'm shooting up over here, so I'm going to continue to do that, but then eventually in the long run we have to level out towards that horizontal asymptote. So that's kind of what my graph is going to look like initially. Alright, now we're not done yet, because now what we want to do is take the absolute value of that graph. So the easy part is anything that is positive y's, they are automatically going to stay positive when you take their absolute value. So these points on here all have y coordinates. Which points on this red graph have y values that are positive? Well, that's anything above the x-axis. So all of these points here have positive y's. So when you take their absolute value, they're going to stay positive. And all of these y's are positive as well. So when you take their absolute value, they're going to stay positive also. So what happens down here for all these points that have negative y values? Well, they're going to turn positive. And when you take something that was negative and you turn it positive, that's a reflection over the x-axis. So all of these points right here, let me use yellow, all of these points right here are going to reflect over this x-axis. So these points here would flip up, have the same shape that this has down here, but now it's being flipped over that x-axis. So everything in black here is your final graph. And notice everything in black here is either hitting the x-axis or positive, which is what we would expect with an absolute value. Okay? All right. The next couple of examples that we're going to do are a little bit trickier. These are going to be square root composite graphs. So we're going to start with some function inside, and we're going to graph that first, and then what we're going to do is take the square root of that graph. So let's start, before we even worry about the square root, let's start by just graphing this inside function. So let's just graph negative x minus 2 squared plus 4. So you should realize right away that that's a quadratic. Because of the negative, it has a reflection over that x-axis, so it's going to be a quadratic or a parabola that's pointing upside down. You're shifting right 2 and up 4. So if we graph that, your starting point normally for a quadratic is 0, 0, but we're shifting that right 2 and up 4. So that vertex is now at 2, 4. And because we don't have any vertical stretch or compression, we don't have to worry about changing our pattern. The only thing we do have to worry about is that it should be pointing down because of the reflection over the x-axis. So normally the pattern would be over 1, up 1. Here we're going to go over 1, down 1 on either side. And then from here it would be over 1, down 3 on either side. So you get your nice U shape pointing upside down. So there's our parabola. Now what we want to do is take its square root. So you have to think about what a square root is going to do. Let's start with the negative values. Can you take the square root of a negative number? No, it's not a real number, and we are only able to graph real numbers. So one nice thing about this is that any y values that are negative, which would be all of these y's here and all of these y's here because they're below the x-axis, you cannot take the square root of those y values. So you lose them. That's what this states right here. So if you have any y values that are negative to begin with, you just lose that whole piece of the graph and it's no longer there anymore. What about 0? Can you take the square root of 0? Yes. Square root of 0 is 0 right back again. So this dot right here has a y value of 0. When I take the square root of 0, it stays 0. Likewise over here, this is a y value of 0. Square root of 0 stays 0. So the zeros stay zeros. So we kept our zeros. We lost our negatives. Now what about our positives? Those are the tricky ones. So let's take this vertex as an example. What's the y value of this vertex right now? Right now it's at a height of 4. Well, what happens when you take the square root of 4? What does it turn into? It turns into 2. So this dot is going to still stay at an x value of 2. All we're doing is changing its y value. And instead of being at a height of 4, now it's going to be at a height of 2. So this point kind of dropped down to there. Now let's take a look at this dot over here, for example. This is at a height of 3. So what would be the square root of 3? Well, that's about 1.7. So it's going to drop down a little bit as well, and likewise on this side. Now let's take a look at some of these points right in here that are less than 0. Say you take this point that's at a height of 1/2. What happens when you take the square root of 1/2? If you punch that into your calculator, and hopefully you have a calculator handy, what you'll see is it turns into about 0.7. So it was at 0.5 before, and now it's moved higher to 0.7. So this little dot that was at 0.5 before is now going to be a little bit higher than it was before. It's going to be at a height of 0.7. And that's true for all of these fractions. So that's what this statement is saying right here. If you have any y's that are fractions between 0 and 1, the graph actually gets higher right around that region. But if the y's are greater than 1 to begin with, like our 4 and our 3, then these y values got smaller. They get lower. So all of these points on the graph above 1 are going to get lower, but all of these points on the graph are actually going to get a little bit higher, and it's kind of tricky to show that. Let me redraw my graph here so you can see what the final graph is going to look like. We have a 0 at 0, and we have a 0 at 4, and that vertex, which was at 4 before, is now only at 2, and it's going to look a little bit wide as we go to the right. And let me show you on top of this what the graph before would have looked like. It would have looked something like this in comparison. Let me adjust my graph. It's hard to show this accurately with the pen that I have to use on this computer. But what I'm trying to show you here is that these points are a little bit above and to the right of that graph in yellow. It kind of bows out a little bit, and then these get a little bit lower. So this graph in black is our final answer. Notice it doesn't have any y values below that x-axis because you can't take the square root of any of those negatives. Okay, so this is kind of tricky. Let's try another one. We'll do a few of these to get the hang of it. Let's take a look at this one. This one has inside of it a rational function, and we're trying to take the square root of that rational function. So how can we do that? First, we need to start with this x minus 1 over x plus 3 and get a good graph of that. Well, because it's rational, you absolutely need to worry about asymptotes first. So where does that denominator want to be 0? At -3. So you're going to have a vertical asymptote at -3. How about horizontal asymptotes? Well, horizontal asymptotes occur at the dominant term on top over the dominant term on bottom, and those are going to cancel out to a 1. So we're going to have a horizontal asymptote at +1. How about intercepts? Well, when you have this numerator equaling 0, that's when the whole fraction will be 0. So that's when you have x-intercepts, and that's going to occur when x is 1. And a y-intercept occurs when x is 0, so if I make these zeros here and here, they go away, and we're left with negative 1/3. Okay, so let's put it all together. We have a vertical asymptote at negative 3. We have a horizontal asymptote at 1. We have an x-intercept at 1 and a y-intercept at negative 1/3. We have a vertical asymptote, so we need to see what behavior is going to happen around it. And remember, this original function was x minus 1 over x plus 3, so that denominator was to the first power. So what that means is near this asymptote, I'm either going to go up on the left, like this, and down on the right, or vice versa. Either I'm going to go down on the left and up on the right. So one or the other, but opposite directions. So to figure out which case it is, pick a test point. So let's say that I wanted to pick something slightly to the left of this vertical asymptote. Since this is at negative 3, something to the left of negative 3 would actually be something like negative 3.01, something a little bit bigger than the number 3, but to the left, since it's negative, it actually becomes negative 3.01. So we're going to plug that in to this rational function and see what sign we get. So if we plug in a negative 3.01 and then subtract 1 from that, it's going to stay negative on top. If I take negative 3.01 plus a 3, that's going to be negative as well. But a negative over a negative turns positive. So as x approaches negative 3 from the left, that means my y's go to something positive, so they have to go to positive infinities. So on the left side of this asymptote over here, I have to be shooting up. Because of that opposite direction thing, this means I have to go down on the other side. So let's connect our dots. These going down have to eventually rise up to pass through my two intercepts and then level off. And over here, I need to level off as well. Okay, now we need to take the square root of this graph. So how are we going to do that? Well, first of all, remember, zeros stay zeros. So the zeros would be anything that crosses that x-axis. So that's right here, and that's going to stay 0. Then negatives you lose. So all of these points here get lost. They are no longer in the graph at all. We don't have any points at all that we're going to be plotting for those points on that original graph. So these points in yellow are just completely gone. No more. Then for the rest of the graph, we need to do that square root. So all of these points right here, notice how high are they? This asymptote right here is at a height of 1. So these are all fractions. And what happens when you take the square root of a fraction? It actually gets bigger. Okay, like square root of a 1/2 turned into a 0.7. So the numbers are actually going to get higher. The y values are going to get higher. So instead of being all these points in red, we're now going to have points that are all still a little bit higher. Now we're not getting too big. We're still staying under 1, but we're getting higher than what the graph was before. Now all of these points right here are above 1. So when you take the square root of something bigger than 1, then the y values get smaller. So for example, these points would all get lower than where they were before. So this graph in black is my final square root graph. So all these y's got a little bit lower than they used to be. All these y's got a little bit higher than they used to be, still under 1, but higher than they were before. This 0 stays 0, and we lose all of these negatives. Okay? All right, let's try another one. Here we want to take the square root of x plus 3 minus 2. So start with this inside part and graph that first. So let's draw the graph. of the square root of x plus 3 minus 2. So that is a square root that's shifted to the left 3 and down 2, because a plus 3 is left and a minus 2 is down 2. So we're going to go left 3, down 2. There's no vertical or horizontal stretches or compressions, so we can use our normal pattern that we would for a square root, which is to go up 1 over 1, up 1 over 3. So here's the graph of our square root. Now we want to take the square root of it. So let's start with our zeros. The zeros are the points on the x-axis. So this is the only zero I have. Square root of 0 stays 0. Then look at your negatives. All of these points are below that x-axis, so they have negative y values. So they are gone. That's no longer in my graph. Then we look at the rest of this graph, and I'm going to look for that point 1, that height 1. It looks like it's right around here a little bit. Let me actually draw this a little bit better so we can see. So you can kind of visualize where that cutoff would be. There's about the point that's at a height of 1. Now the reason I'm sort of pointing that point out is because all these y's that are below 1 actually are going to get higher, because remember, up here, square root of a fraction gets bigger, gets higher. All the points that are above 1, when we take the square root of them, they're going to get smaller. So once we hit this height of 1, all of these points are actually going to get lower than they used to be. So it's, again, kind of difficult to show this very clearly on our graph. Let me see if I can give it another shot. We have our normal graph, which is going to look something like this. Okay, and then what we're doing is we're keeping this 0, we're losing all of those negative pieces, and then where this invisible line would be at a height of 1, all of these points get higher, and then after that line all of our points get below that red curve. So where we hit 1, where we're slightly below it, our black graph should be above the red curve, but after that height of 1, our black curve should be below the red curve. So this one in black is my final answer. Tricky stuff. Let's try one more example. Okay, so this one we want to take the square root of absolute value of 3x minus 6 minus 2. Now before you graph this inside function, this inside absolute value function, please realize that you do have that 3 in front of the x that can be factored out of your x term. So make sure you do that. And then it's my preference to pull that 3 all the way out, because absolute value of 3 just stays 3. So I am allowed to pull that out. So this has a horizontal, or excuse me, a vertical stretch by a factor of 3. Then it's going right 2 and down 2. So let's draw that. We're going to go right 2 and down 2 to get our new vertex of our V shape. And then to get the V's, we need some side points here. So what we're going to do is we're going to go, instead of going over 1 up 1, we're keeping the horizontal the same, but we're stretching the vertical amount by 3. So instead of going over 1 up 1, we're going to go over 1 up 3. And I'm just going to do 2 points there, but it's going to look something like this. Okay? Alright, now we're ready to take the square root of this graph. So start with your zeros. We have 2 zeros. We have a 0 here and a 0 here, and they're going to stay 0 in our graph. Then we're going to lose all the negatives. So all of this point, part of the V that's below that x-axis is gone. It's no longer in my graph at all. And then what we're going to do is we're going to visualize this height of 1. All the y values that are below 1, we're going to be drawing a graph that's actually a little bit higher than that. And it's curving because square roots do curve. They're not straight lines. At 1 itself, square root of 1 stays 1. So these points are going to stay at 1, those two little dots. But then after this height of 1, all these y values are going to get lower. And again, remember, square roots are curving. They're arcing graphs. So it's going to look something like that. So these two little arcs in black would be my final answer. Okay, the last kind of composite graph that we're going to talk about today, we've done absolute values, we've done square roots, now we're going to do reciprocals. So what we're going to be doing on these is taking a graph and then we're going to be drawing it and taking its reciprocal to get our final graph. So in other words, you might see something like this where it's 1 over x plus 3 quantity squared. Now certainly you could just graph this straight as is and think of it as a rational function and graph it that way, and that works. But I'm going to show you an alternative, and especially for some of the later examples, you're going to want to use this process where we do a reciprocal graph to get your final graph if it's a little bit more complicated. So here's what I'm going to do. I'm going to just graph the denominator function first. So what would the graph of x plus 3 quantity squared look like? Well, it's quadratic, and because it's got that plus 3 in there, this is a shift left 3. So it's just a parabola that's been shifted to the left 3 units. So here's my new vertex. Because there are no vertical stretches or compressions or anything like that, I'm just going to use my normal pattern and go over 1, up 1 on the left and the right, and then over 1, up 3, over 1, up 3. Let me make this a little bit better. Alright, not too much better, but there's my parabola. Okay? Now what we're going to want to do is we want to do 1 over this graph. So here's some of the things that we need to think about. Let's start with our zeros on our graph. What happens when you do 1 over 0? What happens to that? 1 over something really, really small gets big. So this is going to go to either positive infinity or possibly negative infinity. And we'll talk about which one of those it's going to be. But 1 over something 0 itself is actually undefined. But 1 over something really, really small does get very, very large. So here's the first thing that's going to happen. You're going to have vertical asymptotes wherever your denominator is 0. In other words, wherever you have zeros on the original graph. So this 0 right here, 1 over it would become undefined, which is going to turn it into a vertical asymptote. So I have a vertical asymptote now at x equals negative 3. And that's what we would have expected from this rational function that we started with. Okay, now let's talk about the behavior around this asymptote. And that's kind of going towards what we were talking about here. If you have 1 over something really, really small, it's going to get big. So think about these points as they travel along this curve. As I move this way along the curve, I'm getting closer and closer to 0 through positive values. So in other words, I'm going to 1 over 0 through positive numbers. That's how I'm going to show that. So I'm getting closer and closer to 0 for these y values, but they're all positives. So what's that going to do? Well, 1 over something really, really small gets big, so this is going to go to infinity, and since all these numbers that I'm getting closer to 0 with are positives, this has to go to positive infinity. So what does that mean? It means as my graph approaches 0 from the right-hand side, this has to approach infinity, positive infinity, in my reciprocal. Okay, let's try that from the other side and we'll see what happens. So this time I'm going to approach the graph, approach that vertical asymptote from the left side. Again, I'm getting 1 over something that's getting closer and closer to 0. All these y values are getting closer to 0, but they're all above the x-axis, so they're all positive. So what does 1 over something really, really small do? It turns big, and since all these are positives, it's got to be a positive infinity. So all these points in green turn into all these big points in black going towards positive infinity. So everything in green turned into everything in black. Okay, so now we know what's happening on either side of this vertical asymptote. Now before we are done, we need to look at what happens at the other extreme. We looked at what happens as we got close to this 0. Now let's look to see what happens as we go this way along our graph. Now think about this one on the right. What is it doing? These y values are shooting up and getting bigger and bigger and bigger. So what happens to 1 over something really big? Well, it's going to get small. There's that inverse relationship. So 1 over something really, really big has to go to something small, like 0. So as these points get really large, all of my y values are going to be getting closer to 0. So all those black points are going to turn into a horizontal asymptote. Same thing on the other side. As these points get really, really large to infinity, 1 over something infinite goes to 0. And these are all positive infinities, so this is going to go to 0 from above, from positives as well. So that's why this is sort of approaching 0 from above, that x-axis. If you connect these two black pieces, then you get your final graph. So here's what the graph of 1 over x plus 3 quantity squared looks like. Just a nice rational function, vertical asymptote at -3, going up to infinity on either side of the asymptote, and it turns out to have a horizontal asymptote at y equals 0. So let me summarize kind of the key points that we talk about here. What we're going to look at is what happens as we get close to our zeros. So here's one conclusion. If your y values are getting closer to 0 through positives, then the reciprocal should shoot up to positive infinity. So that was what we had going on here. These little green pieces here were getting closer to 0 through positives, and that turned into all these really large positive infinity values shooting up towards that asymptote. If your y values are getting closer to 0 through negatives, then you have to shoot down instead of shooting up. So we're going to shoot towards minus infinity. If your y's are going to positive infinity, which were these tail pieces here and here, if your y's are getting big, then in the reciprocal, 1 over that is going to get closer and closer to 0 through positives as well. If your y's happen to be shooting down, like going down this way, then your reciprocal will still be going to 0, but it'll be going to 0 through negatives. So this is kind of complicated. Let's practice some more and you'll get the hang of it. Alright, let's try this next one. So this is one you wouldn't be able to treat as just a nice rational function because you have a square root in the denominator. It's not polynomials. So the only way to do this graph is to use this process that we just talked about. So here's what we do. We start with that denominator, and we need to get a good graph of that, and then we're going to think about what it's going to do when we do 1 over every single y value in that graph. So how do we graph this? First of all, notice there is a coefficient in front of that x, even though it's just this little minus sign. So be really careful. I like to switch the order around so that I see that negative a little bit more clearly, and then I like to factor it out, and that's going to mean that instead of going to the left 5 because of this plus 5, we're actually going to be going to the right 5 because it turns into a minus. What does this negative right here do? Because it's inside of the radical, it's a reflection, but it's a reflection horizontally. So this is a reflection over the y-axis. What does that minus 5 do? We said that goes right 5, and the minus 1 on the outside goes down 1. So let's put it into our graph. we're going right 5 and down 1. So there's our starting dot for our square root. Normally, square root of x goes up 1 over 1, up 1 over 3, and it arcs to the right. But now we have this reflection over the x-axis. So this is actually going to need to arc to the left. So we need to go up 1, left 1, up 1, left 3. So that's the pattern that I want to apply over here to this starting point. I want to go up 1, left 1, and then I want to go up 1, left 3. So there's my square root. Now what we're doing is we're going to take 1 over that whole big square root. We're doing a reciprocal graph. So first thing to look at are the zeros. Okay, here's my 0 on my graph. Now what happens if you do 1 over 0? That's undefined. It doesn't exist. So that is going to automatically turn into a vertical asymptote. So any zeros that you have turn into vertical asymptotes, dashed lines. Now what we want to do is see what happens on either side of that asymptote. Either we shoot up or we shoot down, and we need to figure out which way we're supposed to go. So the way that you figure that out is you look at what the graph is doing as we get closer and closer to the 0. So here on my graph, look at these little green dots here. They are going closer and closer to 0. Are they getting closer and closer to 0 from above the x-axis, in other words positives, or are they getting closer and closer to 0 from below the x-axis, in other words negatives? These are all above, so they're going through positives. 1 over something very small gets very big, and since these were through positives, this has to go to positive infinity. And what that means is that on the left side of my vertical asymptote, I have to be shooting up towards that positive infinity. So this tells me which way to go up. Now let's do the other side of my 0. So look at all of these dots. They are also getting closer to 0, but every single one of these dots down here is below the x-axis, so it's a negative value. It's a negative y value. So we're doing 1 over something that's getting smaller and smaller, so that's still going to blow up, but because they're negative, they're going to blow up in the negative direction. So that means I want my graph to shoot down to minus infinity for all of these points, like this. Now let's finish off this right side for a moment, because look at this dot right here. This is just a starting point for this square root graph, this little red dot. And right now it's at a height of -1. So what are we doing to this graph again? We're doing a reciprocal. So if this point is at 5, -1, what we're doing is we're taking 1 over that y value. That's what this formula right here said to do. Take 1 over all of these y values. So what's 1 over this y value? Well, this y value is -1. So 1 over -1 is going to stay -1. In other words, for this particular dot, the reciprocal of this y value is that same dot itself, which means that I am going to stop right there, and these points are going to shoot down towards that minus infinity that we know we're supposed to have on the right side of that vertical asymptote. So for this particular graph, that starting point stayed where it was. Okay, now we have to see what happens over here. So what's happening to all of these y values? They're slowly but surely getting higher and higher and higher. This graph is growing. It's just growing pretty slowly. So all of these y values here are getting bigger and going up towards positive infinity. So what happens if you have something that's going to positive infinity and you take its reciprocal? In other words, what happens to 1 over positive infinity? What does it do? Well, 1 over something big gets small. So 1 over something infinite is going to go to 0. And since all of these were positives, we're going to be approaching that 0 from above the x-axis as well, through positives as well. So what that means is these points here turn into a horizontal asymptote at a height of 0 through positives. I don't want to cross that x-axis. All of these y's should stay positives because 1 over all of these positive y's is going to stay positive. So the extreme tails turn into your horizontal asymptote. The zeros turn into your vertical asymptotes. So the graph in black is my final answer. Okay, we have one last example, another reciprocal. Let's give it a try. So this time we want to take 1 over this absolute value function. So start with the denominator and get a good graph of that first. This is just a nice absolute value, a nice V. We're going left 2 because of the plus 2 and down 3. So let's get that vertex, left 2, down 3. There's no vertical stretch or compression or anything like that, so we can just go over 1, up 1, over 1, up 1, over 1, up 1, and so on to get several dots here. I'm going to keep doing my dots until I get to my zeros, because zeros are important when we're doing reciprocals. So these look like I'm going to have 2 zeros, 1 at 1 and 1 over here at -5. So here's my absolute value. Now the reason I wanted those zeros is because now we're going to do 1 over, and 1 over a 0 becomes undefined. So first thing right away, any 0 that you have on your initial graph turns into a vertical asymptote. That's step 1. So find your zeros, turn them into a vertical asymptote. Step 1. Step 2, find out what happens on either side of your vertical asymptote. So either this is going to go up or it's going to go down, and we need to figure out which way. So here's how you figure that out. You look at all the points on your graph on the left side of that asymptote. All of these are getting closer to 0 and they're all positive. So when I do 1 over something going to 0 through positives, that's going to turn big, and since these are positives, I need to be going to positive infinity. So all these points in green here turn into all those points in green when I take their reciprocal. Okay? Likewise, on the other direction, this way, I'm still getting closer to 0 as I drive along this curve towards that 0. So I'm still going to 0, but all of these y values are now negative. So when I do 1 over that, it's going to go and blow up, because 1 over something small gets big, but it's going to stay negative. So all these points on the right side were negative, so that means this has to go to negative infinity on the right side. Okay, let's do it for the other vertical asymptote. All of these are negative points going to 0, so that's this case again. So I have to shoot down. All of these y values are positive, so that's this case, so I have to shoot up. Okay, all that really matters is whether the y's are positive or negative. If they're positive, you want to be going up to infinity. If they're negative y's, you want to be going down to infinity. All right, we know what's happening on either side of our asymptote. Let's look at the extreme behavior. So let's see what happens as I go this way. So what's going on as I go this way? What are these y's doing? Well, they're getting bigger and bigger and bigger, and they're getting bigger as we approach positive infinity. So all of these y's here are going to positive infinity. So what happens when I take the reciprocal of that? 1 over something big gets small, and since these are positive, this needs to go to 0 through positives as well. In other words, from above. So all of these points in orange here become points closer to 0 from above. Let's look at the other side. All of these are going to infinity as well, positive infinity. So 1 over that goes to 0 from above. So likewise on this side, you're going to have a graph that does the same thing on the other side. So you've got a horizontal asymptote at 0. Okay, we're almost there. We can go ahead and connect this horizontal asymptote with that shooting up, and we can connect this shooting up with this horizontal asymptote, but we're sort of missing some stuff here. We know that this shoots down, and we know that this shoots down, but what's going on right in the middle? So now we need to figure that out. These are not going to infinities or zeros right here, so these are actual numbers. So we can figure out where this goes to. What is the y value of this vertex? Right now, it's at -3. What are we doing to get this graph in black? We're doing a reciprocal. So if this is -3 for that y value, our reciprocal would turn that into 1 over -3. So this black dot moves to a height of -1/3. So this becomes the new y vertex, if you will. So all we have to do now is connect that down to these two pieces that we know should shoot down. So this vertex in our V got pushed up to -1/3 by just taking 1 over whatever this y coordinate happened to be. So this graph in black is my final solution. Alright, these are tricky. They take a lot of practice, but a lot of the instructors for this course do require that you have really good graphing skills, and will ask some tricky questions like these involving absolute values of a graph, square roots of a graph, or reciprocals of a graph, as well as your basic transformations. So please practice them. Good luck! This concludes the lecture on composite graphs.